this lecture I'll develop the tangent, normal, and binormal vectors for the helix, and also compute the curvature and the torsion. The helix is a very nice space curve to use because the arc length has a closed form solution that allows you to put the equations for the helix into the arc length parameterization, where all these calculations are easier. Let's start with a look at a helix and also at the classification of helices. So what we have here is this helix starting at this point, and notice if you trace it out how it's going, assuming it's going in this direction, that it's climbing up the z-axis. Now this is a right-handed helix because if you put your thumb along the z-axis, your fingers would curl in the direction that the helix is turning. They would curl in this direction. Obviously you could have a left-handed helix. It would be going like this. You can see whether it's right or left-handed by looking at the equation. Here's the equation for a right-handed helix. But this is the standard form. You have on here alphas multiplying the cosine and sine for the ij term. Alpha is the radius of the helix. That would be the distance from the center here out to the edge. Beta is a scaling for the helix. It tells how long it takes, how much distance in z it takes to get around one turn of the helix. One turn of the helix is 2 pi times beta. So here again is the equation for a right-handed helix. Here's the equation for a left-handed helix, both of them going along the z-axis. You start with sine for the I term, otherwise it's cosine for the I term for the right-handed. To see how this would work, you can plot a few points. Just do it in the plane. So here's your xy plane. Okay. If I start here when t is 0, then the first term is alpha, and the j, forgetting beta for right now, the j term is 0, the I term has value alpha, so we're sitting here at alpha. Okay. So this is that t equals 0. Now let t advance to pi over 2. When t is pi over 2, the I term is 0, but alpha sine t is alpha. That's the j term. So now you're up here at pi over 2. At pi, r would be minus alpha in the I direction plus 0 in the beta direction, so here you are at minus alpha. So you see if you connected the dots, you're going in this direction, and that's considered a right-handed helix. It's going counterclockwise. Now I'll do the same thing for the left-handed helix so you can see the difference. Looking at the left-handed helix now, and first we'll let t equals 0. When t equals 0, of course the I term is 0, but the j term has a value alpha. So here's t equals 0 right here. Now let t advance to pi over 2. At that point r would have the value alpha I. So now you're down here at t equal pi over 2, and you can see whereas for t equals pi, you're at minus alpha, and you can see now you're going in a clockwise direction. So this is called a left-handed helix, or clockwise helix, and here's your right-handed helix. Both of these are going along the z-axis. You could have the helix going along the x-axis. You just see you move the terms around. Initially I said that the arc length function had a closed form solution, so I'll show that here. This is the general form for the arc length function. We have dx by dt squared. You can remember the x was alpha cosine t. Right. So if I take the derivative and square it, of course the derivative is minus alpha sine t, and I square that. Then for y was alpha sine t. Here's the derivative is alpha cosine t. We're going to square that, and then the z component was beta t. Taking its derivative, we just get beta. So when we square this, we'll end up with alpha squared times sine squared t plus alpha squared times cosine squared t. And we make liberal use, as we always do, of the Pythagorean identity that sine squared plus cosine squared is equal to 1, and here's the result. We have this constant, alpha squared plus beta squared times d tau integrated from 0 to t. This is the solution for the arc length function along the helix. And as you know, that's remarkable. There aren't very many functions that do have closed form solutions for arc length function. So to create the arc length parameterization for the helix, remember we have this closed form solution s is the square root of alpha squared plus beta squared times t. Just solve for t. T equals s divided by root alpha squared plus beta squared, and substitute that into the equation for the helix. So the t's get replaced by s divided by alpha squared plus beta squared, a square root of that. And there's your arc length parameterization. So here's an example. Say the helix has a radius of 8 and the beta is 6. And you would like to put that into the arc length parameterization form. Well, the arc length was s equal to the square root of alpha squared plus beta squared times t, while alpha squared plus beta squared, the square root of that is 10. So we have s equals 10t for this particular helix. So here t equals 10 over s, and that's what we substitute in, and you can see those terms right here. So t gets replaced by s divided by 10. And now this is the arc length parameterization for a helix with a radius of 8 and a beta of 6. Now on the homework it asked you to verify that for this arc length parameterization that you've written, that the velocity is 0. Remember, the arc length parameterization is called a unit velocity curve because the velocity is 0. So we have to take the derivative with respect to s of this arc length parameterization, and it looks a little bit messy, and I had to write it on 3 lines. Here's the I component, the j component, and the k component. What we're interested in, of course, is the magnitude of that. For the example that we're doing, I just substituted here so you can see for that helix that had a radius of 8 and a beta of 6, this is what you get for the velocity. It's fairly straightforward. Okay, but we now need the magnitude, and that should be 1. Alright, so we're really looking for the magnitude. We want to show that that is 1 because we have an arc length parameterization. So in this case, of course, it's just as well to compute the magnitude squared, which is the velocity dotted with itself. We end up with the same kind of terms similar to what we had before. We've got a cosine squared term and a sine squared term, both of them multiplied by the same coefficients, which can be, or same amplitudes, which can be put out, factored out from them, and then we use sine squared t plus cosine squared t is equal to 1, and then we get our answer that the velocity of this curve, of this arc length parameterization of the helix is indeed 1. Here's a result in general. You can work out the terms as well. So because this is an arc length parameterization, once we take the derivative, which we just did, we have the unit tangent vector. We don't have to create the unit tangent. It already is a unit tangent. And here is the result for the unit tangent for a helix in general. Now we're looking for the normal and the curvature. So we take the derivative with respect to s of the unit tangent. Its magnitude is the curvature. The unit vector is the unit normal. So when we take this derivative, notice, remember the z term was beta t in the k direction. The first derivative gave us beta, and now with this next derivative we end up with a 0, so we only have 2 terms, which is minus alpha over alpha squared plus beta squared times the cosine, and then minus alpha over alpha squared plus beta squared times sine. magnitude of this derivative is the curvature, and it doesn't take much to work out these steps. We get alpha over alpha squared plus beta squared, and that is the curvature of a helix. So in the example that we had, alpha was 8 and beta was 6. Here's the curvature, 8 over 100. The normal vector is that unit vector created from the first derivative of the tangent. And again, just notice the signs. Other than that, it's pretty straightforward. So now we're looking for the torsion. For the torsion, first we create the binormal vector, which is a cross product of the tangent and the normal. So I wrote this in fairly small script so I could fit it all on the page. Remember, the normal had a 0 for the z component, and because there was no parameter associated with it, the z component for the tangent was a constant. So you have the z here, which is helpful, and the rest of the terms are fairly straightforward. They were just derivatives of sines and cosines. Then we take the result, we get the b vector. We're going to have to take its derivative again to find the torsion. So I take the derivative of the vector b, which is actually very small here. I could have made that font a little bit bigger. And we need its magnitude. Again, we make use of the Pythagorean theorem for trig functions to get the sine squareds and cosine squareds out of the picture. And here's the torsion, minus beta over alpha squared plus beta squared. So the torsion is minus 6 over 100. And if we took the unit vector associated with this derivative, we would find that it is the same as the normal that we calculated early using the tangent vector. And here are the equations in the Frenet-Serre form, the matrix form. We have the derivatives, and I've written them with primes because these are the arc length derivatives for this for the helix. And we'll have the skew symmetric coefficient matrix, and then the vectors themselves. So in this case, for the helix, the curvature is alpha over alpha squared plus beta squared, and the torsion is minus beta over alpha squared plus beta squared. So of course we can factor out the denominators, and here is the Frenet-Serre frame for the helix. Now if you have some numbers, it's pretty easy to substitute those. Okay, in this case we have 1 over 100 because our alpha was 8 and the beta was 6. So then the matrix is 0, 8, 0, minus 8, 0, 6, 0, negative 6, and a 0, and then we have our t, b, and n vector. And that's it for the helix. So I think there was a homework problem concerning the helix, and these are the different parts. So you need to work through it, write down the steps. I think by the time you get through doing that example fairly well, you will have good familiarity with deriving these t, b, and n vectors and finding the torsion and the curvature for space curves.